Okay, so let's review the basic steps in analyzing NMOS circuits. I modified this a bit from the last time. So the first step is to determine VGS from the gate circuit. So we determine VGS from the gate circuit, knowing that our gate current is equal to 0. We compare VGS with the threshold voltage VTH. If VGS is less than VTH, then we know that the NMOS transistor is not conducting and is cut off. And therefore, your drain current, which is equal to your source current, is equal to 0. And from that information, you can now compute for the rest of the circuit quantities that you need. Now, if you find that VGS is greater than or equal to VTH, then there are two possibilities. Either the transistor is in saturation or the transistor is in linear mode. So we have to test these two possibilities. The more convenient one to test is whether the transistor is in saturation or not. So usually that is our first assumption, that the transistor is in saturation. And we apply the formula for determining drain current in saturation. And that formula depends only on the gate to source voltage. It does not depend on the drain to source voltage. If you recall our VI characteristic, okay, for a particular gate to source voltage, our characteristic looks like this, okay, where we said that this is our linear region and this is our saturation region. And if you will note, saturation, the drain current, so this is our drain current, this is our drain to source voltage. The drain current will not depend on the drain to source voltage. In fact, the drain current is practically constant. It's practically constant. It only depends on the value of your gate to source voltage. This is in saturation. So here, it only depends on the gate to source voltage. So we solve for VDS by applying KVL to the drain to source path. And then we check. We have to check our assumption. So how do we check? Okay. So the transition from linear to saturation happens at VDS sat. And this is equal to VGS minus VTH. VDS sat is equal to VGS minus VTH. If VDS is less than that, then that's linear. If VDS is greater than that, then that is saturation. So if VDS is greater than VGS minus VTH, that means nandito tayo sa right side. Nasa saturation tayo. Okay. Pag nakita natin na na-satisfy ito, then our assumption is correct, and the value that we calculated for ID using this formula is valid. Okay. Now, if we find that VDS is less than VGS minus VTH, ibig sabihin na dito tayo sa kaliwa, we are less than this quantity, nandito tayo sa kaliwa. And therefore, we're in the linear region. And therefore, this equation that we initially used is wrong. We should have used this equation instead. Problema lang nitong equation na to, the drain current now depends on two things. It depends on VGS, and it also depends on TDS. So if you take a look at this, okay, the value of ID is now also a function of VDS. Of course, it is also a function of VGS. We have to combine this equation with the KVL equation of the drain to source path to determine ID. So we end up usually having to solve two equations into unknowns. And that solution often ends in a quadratic equation. It often ends in a quadratic equation. Now, the thing I added to this slide is this last statement. Alternatively, you can use the RDS on approximation to determine the desired circuit quantities. But remember, this is an approximation. That is an approximation. In other words, the values that you get are not very exact. But for all, maybe for practical purposes, it might be accurate enough, no? But you have the danger that it is not very exact. Okay. So you remember our RDS on approximation, ito, no? Okay. For small values of VDSQ, we can approximate RDS on to be equal to 1 over K multiplied by VGS minus VTH, where RDS on is the slope of this particular line. The problem with the RDS on approximation is depending on where you are, the slope slightly changes. Depending on where you are in the curve, the slope of this line slightly changes. That's why it's just an approximation. Okay. Are there any questions with regard to this before I proceed? Any questions? Okay, no? So, by the way, no? Just some tips, no? Tips. Okay. For small VGS, for small VDS, okay, the probability that NMOS is in linear region is higher. No? Kita naman dito sa graph na to, no? Pag maliit yung value ng VDS, the probability that we are in the linear region is higher. No? Consequently, for large VDS, no, the probability is higher that NMOS is in saturation. So that will help you make an initial assumption. Kung maliit yung value ng VDS, no, then your initial assumption might have to be it is in linear mode. Kung malaki yung value ng VDS, then your initial assumption might have to be that it is in saturation mode. If you have no idea, then just like here, if you have no idea, usually we start with the assumption that the transistor is in saturation. Okay, then we went ahead last Tuesday. I gave this problem, no? So the transistor has K equal to 0.5 milliamperes per volt squared and a threshold voltage of 3 volts. I wanted you to determine the drain current and the output voltage of this particular circuit for various values of input voltage. Okay, and we already showed that it's obvious that if the input voltage, which is VGS, is less than 3 volts, the threshold voltage, then your drain current is 0 and your output is just VDD, which is 12 volts. And then we showed that for these two, for 4 volts and 6 volts, we started with the initial assumption that the transistor was in saturation, and we validated that it really was in saturation. Na-validate natin yon, no? Okay, and we came up with these values. Now for 8 volts, okay, we started with the assumption that it was in saturation, but we found out later after checking na hindi pala siya saturation. It is in the linear region. So we had to do a recalculation. We did a recalculation using this formula. Okay, and then these are the values that we got. In fact, the recalculation is here. No, this is the recalculation. When we did a recalculation, we had to combine two equations. We had to combine here, no, where we saw that the mode was linear, we had to combine two equations. When we did, we came up with a quadratic equation which has two roots. Okay, so from the two roots, we had to choose which is the correct value of VDS. And that is based now on the fact that we had to base it on the fact that we assume that it is in linear mode. No? The other root was in saturation mode. And then we were able to compute for the value of I sub D, which is 4.73. No? So yun yung pinasok natin dito. Okay, I'm going to leave it up to you to do this too. So obviously, your transistor is now going to be in linear mode. No? From this point onward, it's going to be in linear mode. No? Because if you notice, the value of VDS is getting smaller and smaller. So I expect the value of VDS here to be even smaller, okay? Even smaller, whereas the value of VGS is large, and therefore it's very unlikely that VDS will be greater than VGS minus VTH. So just do that. No? What I want to focus on right now is this. No? At what input voltage does the transistor transition from saturation to linear? So let's try to solve this. No? At what input voltage does the transistor transition from saturation to linear? So when does the transition happen? So we want to determine transition from saturation to linear. Okay, this happens when VDS is equal to VGS minus VTH. It happens at this point, no? When VDS is equal to VGS minus VTH, then at this point, we are transitioning from the linear region to the saturation region. Okay? Now, the saturation equation still applies. No? What is our saturation equation? You have I sub D is equal to 1/2 K VGS minus VTH squared. Okay? But we already established that this one, VGS minus VTH in the transition, is equal to VDS. Okay, so this is actually now equal to 1/2. Now what is K? Ano ba yung K? K is 0.5, no? So 0.5 M, okay, VDS squared. K, 0.5 VDS squared, no? Or this is now 0.25 VDS squared. That's ID. Okay, but if we apply KVL to the power supply drain to source path, power supply drain source path, we can get a second equation, and that is ID is equal to VDD. So this is one equation. ID is equal to VDD minus VDS over RD. Okay, so this is 12 minus VDS all over 2K. So we can equate these two. So we have 0.25 VDS squared is equal to 12 minus VDS over 2K. So this ends up being a quadratic equation. Okay, so this is now 0.5 VDS squared, okay, plus VDS minus 12 is equal to 0. If you solve for VDS using your polynomial calculations in your calculator, you're going to get two values. The first one is 4 volts. And the second one is an imaginary quantity. The second one is an imaginary number. So of course, we know that it cannot be an imaginary number. It has to be a real voltage. No? And therefore, VDS is equal to 4 volts. So what are we saying? No? Balik tayo rito. That transition from linear to saturation happens for the problem I stated earlier when the value of VDS here is equal to 4 volts. Okay, so I provided now all the answers here. Like I said earlier, try this on your own. You should be able to do this on your own now. We did all of this, no? But I added 2 pieces of information to this table. Now, this is the first piece of information that I added. 3 volts is when the transistor transitions from cutoff to saturation. So nauna yung cutoff, nauna dito cutoff. Tapos habang tumataas yung VGS natin or our input, pumapasok siya sa saturation. And when does that happen? That happens when your input voltage is 3 volts kasi yun yung threshold voltage natin. No? Below 3 volts cutoff, above 3 volts, nagko-conduct na yung MOS natin. Okay. And then beyond 3 volts, we see that it is now in saturation. Kailan siya magda-transition from saturation to linear? So we just computed that here. That happens when VDS is equal to 4 volts. And if I compute for I of D, that corresponds to 4 MA. You can use this formula to compute for I of D. So 12 minus 4, which is 8, divided by 2K, that's 4 MA. So this is the transition from saturation now to linear. Okay, so ganyan yung trend niya, no? Umpisa siya cut-off, transition to saturation, and then transition to linear. If I plot what we call the transfer characteristics, that's a plot of the output versus the input. So what does this allow us to do? For any particular input voltage, kitang-kita natin what the output voltage is going to be. So if I just plot these points, the input or the output, itong output versus my input. So it starts at 12 volts cut off. When my input is 3 volts, this is now 3 volts, I start to see some conduction, and your transistor now enters saturation. So now this is saturation, this is saturation, this is saturation. And then when your input is 7 volts, that's when it starts now going to linear. So this is now linear, linear, linear. Okay, these are just approximations. The output varies almost linearly with the input when the input is between 4 and 7 volts. So between this point and this point, if you take a look, the output varies almost linearly, almost in a straight line. In this particular region, a change of 3 volts at the input results in a change of almost negative 7.5 volts at the output. So if I take a look, this is 3 volts. This is 3 volts. And this one, this is 7.5 volts. And then it is negative because as your input is increasing, your output is decreasing. And we can use now this circuit to amplify signals. We can use this circuit to amplify signals. So when my input is between 4 and 7, so for example, ganito, let's say my input is between 4 and 7. Okay. So between these 2 points, my output is between approximately 11.5, My output is between 11.5 and 4. Okay. So tignan natin, when when my input is at 7, my output is at 4. When my input is at 4, my output is at about 11.5. So if my input looks like this, my output will look like this. As you can see, there's a gain. The peak-to-peak value of this particular signal is 3 volts, and the peak-to-peak value of this particular signal is 7.5 volts. It is an amplifier because whatever information contained in this signal can be retrieved from this signal. So this actually is a circuit of a very simple NMOS amplifier. So if you will recall, the BJT, we showed the same thing, that the BJT can act as an amplifier. Okay, but inherently the gain of a BJT amplifier is larger than the gain of an NMOS amplifier. Okay. Any question with regard to this? So this is just to illustrate how the MOS transistor can act as an amplifier. So we call this the common source configuration. If you recall, in the BJT, we had what we call the common emitter configuration. So ang tawag naman dito is common source because your source terminal is made the reference of the voltages in the other voltages in the circuit. Now there are other configurations. Meron tayong common gate, meron tayong common drain. So this is not the only NMOS transistor configuration. We're not really going to go deeply into the transistor as the NMOS transistor as an amplifier in this course. You're going to take that up more deeply in your next course, which is EEE 131. So this is just to give you a flavor for how an NMOS amplifier works. Okay, just like your BJT, your NMOS transistor can also be used as a switch. Say we have a load. That load is supplied by a voltage VCC. We can use this as a switch. No? The switch can either be open or it can be closed. How do we open the switch? To open the switch, we just make sure that VGS is less than our threshold voltage. Because if VGS is less than our threshold voltage, then this is equivalent to an open circuit. And therefore, no current will flow through my load. Okay. Now, how do we make the NMOS transistor act as a closed switch? First of all, we have to operate it in the linear region. If we want it to act as a closed switch, we have to operate it in the linear region. Why? No? Because a good switch has a very small voltage across it. And if I go back to, I keep going back to this, no? Something here, no? We want the voltage across the switch or VDS, we want that to be small. No? We want that to be small because a good switch, actually a perfect switch, has 0 voltage across it. So we have to operate it in the linear region. Excuse me again for forwarding. Okay, to operate it in the linear region, we have to make sure, of course, that VGS is greater than or equal to VTH. That goes without saying. And then we have to make sure that it is left of that line defining the transition from linear to saturation. So VDS has to be less than VGS minus VTH. On the other hand, we should also choose a value of VGS such that RDS on, the drop across RDS on, so the voltage drop, remember, no, in the linear region, we can model our transistor as a resistor. So we choose VGS rather, so that RDS on, okay, will be very much smaller than the load resistance, so that very little voltage will be lost across my switch. So I have an example here. Example. An NMOS transistor with K equal to 10 milliamperes per volt squared and VTH equal to 1 volt is to be used to connect a 500 ohm load to a 10 volt supply. So yung normal conditions, under normal conditions, we would have had a So this is my load, no? This is my load. We would have had a 10-volt supply here. And then you would have had a switch here. Okay. A manual switch here. Okay. That's how we would have done it under normal conditions. Now, what if you want an electronic signal? So the point is, we now want an electronic signal, okay, to control this load. So one option is, you already know, you can do it with a BJT. Another option, you can do it with an NMOS transistor. So how do you do that with an NMOS transistor? Okay, this is your load. This is now your supply, 10 volts. And then here, you put your NMOS. You put your NMOS transistor. And then this is now your Vin. Okay. So if Vin is less than VTH, okay, your load is off. Okay. Now, the problem is this, no? Determine the minimum value of VGS. So in this particular case, Vin, which is equal to VGS, determine the minimum value of VGS that should be used to turn on the load if not more than 5% of the supply voltage should be lost across the transistor. So when the load is on, no, when the load is on, what do we have? No, we have our load, and we said that this was 500 ohms. We have RDS on. Okay, so we're now using the alternative. No? This is the alternative for determining the current using the RDS on approximation. No? Using the RDS on approximation, and then this is now your 10 volts. Okay, and I want to make sure that this voltage, which is actually VDS, okay, is less than or equal to 0.05, no, 5%. 0.05 times 10 volts, no? Which is equal to 0.5 volts, 0.5 volts. We want to make sure that VDS is less than or equal to 0.5 volts. No? Meaning to say, worst case condition, ang makukuha ng load natin imbis na 10 volts is 9.5 volts. Pero siguro naman okay lang yun, ano? Maybe it will still work properly at 9.5 volts. After all, usually loads have a voltage tolerance. Okay, so let's use the RDS on approximation. No? So we know that RDS on is approximately equal to 1 over K VGS minus VTH. 1 over K VGS minus VTH. Just a while, no? Yeah. Okay. Now from the point of view of it being a resistor, okay, if you only have 0.5 volts across it, okay, you can compute for the minimum value of RDS on using voltage divider. I need another sheet. So, balik tayo, no? We have 10 volts. This is my load, which is 500 ohms. This is RDS on. Okay. This is VDS. Okay, using voltage divider, okay, VDS is equal to 10 multiplied by RDS on all over 500 plus RDS on. That's using voltage divider. Okay, and I want VDS to be less than 0.5 volts from here. No? I want VDS to be less than 0.5 volts. So in effect, 10 RDS on over 500 plus RDS on should be less than 0.5. If I compute for RDS on should be less than 500 over 19 ohms. But what is RDS on? No? RDS on is approximately equal to this, right? It's approximately equal to this. No? So actually 1 over K VGS minus what is VTH? VTH is 1 volt. That's RDS on. Should be less than 500 over 19. Okay. And if I compute for VGS, okay, I'm going to get VGS should now be greater than 4.8 volts. So in answer, what is the minimum value of VGS? The minimum value of VGS should be 4.8 volts. That is the minimum value of VGS. So this is based on the RDS on approximation. Okay, alternative solution. No? And the alternative solution is using the current equation in the linear region. Okay, what is that? No, the current equation in the linear region, you have ID is equal to K VGS minus VTH minus 0.5 VDS multiplied by VDS. Now let's solve for ID, assuming VDS is equal to 0.5 volts, no? Because that is the maximum value we will allow VDS to be, 0.5 volts. No? So at 0.5 volts, ID is equal to K. Ano ba yung K natin? K is 10. No? 10. VGS, VTH is 1 volt. 0.5 VDS is 0.25 multiplied by 0.5. Okay? That's ID. So this is one equation. Okay. Now, what is our second equation? The second equation is this one, no? The KVL here, no? In other words, what is ID? ID is equal to VDD minus VDS over RD. That's 10 minus 0.5, right? Yeah, that's 10 minus 0.5, that's VDS, over 0.5 K. When you're using MA, then you have to shift to K, because this is in milliamperes per volt squared, and therefore, just to be consistent, our resistances should be in kilo ohms. Okay. So this is now 9.5 over 0.5 K. This is my second equation. I can combine these two, okay, to come up with the value of VGS. And I'm going to get, if I combine these two, I'm going to get VGS is equal to 5.05 volts. So may konting difference dito, no? Well, there's a difference of 0.25 volts, no? Now this is supposed to be more accurate. No? Because when we derive this equation for RDS on, we disregarded one term, we disregarded a term here. Let's go back to that. Saan ba yan? Here, no? So the expression really for RDS on should be this. Merong term na ganito, no? But then because most of the time we don't know what the value of VDS is, we just assume that this is negligible, and this becomes our approximation for RDS on. But actually, RDS on will be slightly larger than this. Why? Because of this term. This term will make the value of RDS on slightly larger. So yun yung lumalabas dun sa example ko. No? Okay. Because RDS on is slightly larger than this, then the value of VGS would have to be larger. The value of VGS would have to be larger. Okay. Any questions? Any questions? Okay, I have two additional exercises here. I didn't really intend to go through this in detail, but maybe we can outline the solution and leave it up to you to work it out completely. So here is an exercise. So given VTH is equal to 1 volt, K is equal to 2 milliamperes per volt squared, find ID, VGS, and VDS. So this is ID. This is ID. Okay, this is VGS. Okay, and then this is VDS. Okay, this is VG. Now, warning, no? Common mistake. I see students making this mistake a lot of times. VGS is not equal to, VGS is not equal to VG. The value of the voltage here is not VGS. Why? Because you have a source resistance. Kung wala nitong source resistance, then VG and VGS are equal. And I see students make that mistake all the time. So VGS is not equal to V sub G. Okay. Now, it's very easy to compute for V sub G. And the reason for that is this. No? What is the value of this current, I sub G? Can somebody shout it out? Ano yung value ng I sub G? Anyone? Yeah, that's right, no? That's right, Team C. It's 0, right? Sabi natin, at steady state, basta DC, your gate current is always equal to 0. If I sub G is equal to 0, effectively, the 60K and the 40K resistors are in series. No? Or since I sub G is equal to 0, your 60K is in series with your 40K. No? And therefore, what can we use to determine V sub G? What formula can we use to determine V sub G? Can I hear someone else?
Voltage divider po.
That's right, no? So you can use voltage divider to determine V sub G. No? By the way, no, I'd like to mention something about that. No? Kasi madaming nagtanong sa akin through email when they were trying to solve the BJT problem. No? Kasi may yung BJT problem, no, na there was a BJT problem, something like this. Okay. I can't remember kung may ganyan, ano? Well, let's say ganyan, ano? Okay. Tinatanong nila, no, bakit mali yung sagot nila? They used voltage divider to determine the voltage here, no, sa BJT. And the obvious answer is you cannot use voltage divider here in a BJT because this current, IB, is not equal to 0. No? If IB is not equal to 0, then these two are not in series. And therefore, hindi mo pwedeng gamitan ng voltage divider to determine V sub B. Okay? So, yun, no? A number of students asked me that question. No? Why was their answer wrong? And this is their solution. Ginamitan nila ng voltage divider dito. No? Fortunately, sa MOS, because I sub G is equal to 0, no? Because this is equal to 0, you can use voltage divider to determine V sub G. So V sub G is just equal to 5 multiplied by 40 over 40 plus 60. And this actually ends up just being 2 volts. No? Okay, this will take up 40% of the 5 volts, and this will take up 60% of the 5 volts. So this is 2 volts, and this is 3 volts across it. Okay, remember that VG is not equal to VGS. Okay. You have a voltage here, VRS. Okay, this is also ID. If you apply KVL to this particular loop, what are you going to get? You're going to get VG minus VGS minus VRS is equal to 0. Or VGS is equal to VG minus VRS. But VRS is equal to ID times RS. So VGS, okay, is equal to 2. VG is equal to 2. So minus ID times RS is equal to 1K. Unfortunately, we have 2 unknowns here. So we cannot solve this because we have 2 unknowns. Now, where do we get another equation? No? What is our other equation to be able to solve for the value of ID or the value of VGS? Anyone? Anyone? Ano yung isang equation na dapat natin gamitin? Okay. By the way, no, you have to make an assumption, no? Okay, if we assume saturation, so hint na yan, ano? Assume saturation. So what is our equation now? Di pa rin nyo alam? Anyone? Okay. If you assume saturation, what is your saturation equation? You have ID is equal to 1/2 K VGS minus VTH squared. So this is 1/2 times 2 VGS minus 1 squared. So this is equation 1 and this is equation 2. So you can solve for VGS and ID. Okay? But what do you have to do after solving for VGS and ID? Siguro ito, medyo alam na nyo. What do you have to do? Can I ask Mel, anong kailangan gawin pagka-solve ng VGS at saka ID?
Check for, check for, gosh. Pag nasolve na po sa yung VGS tsaka ID.
Yeah, no, tama ka, no? What will you check for? You check that this assumption is correct.
Yeah. Yes, sir.
Okay. So pagka-solve mo for VGS and ID, you just have to check that this assumption is correct.
It's correct.
Yun lang, no? If the assumption is correct, tapos na yung laban, ano? You already have the quantities that you're looking for, no? Alam mo na yung ID, VGS, yung VDS madali mo na makukuha, no? Because if you know ID, you know the voltage here, you know the voltage here, you know this voltage, makukuha mo na yung VDS. Ang problema is if you find that it is in linear, no? So if it's in linear, then you have to switch your equation, no? You have to switch to the linear equation, in which case madadagdagan ka ngayon ng isa pang unknown, and that is VDS. But then you can form now a VDS versus ID equation using this circuit. So you will have an additional equation that you can use to eventually solve for I sub t. So yeah, I'm not going to go through the entire solution. So but in a gist, that's how you solve this problem. And then you can also try this problem out. No? So ito naman, ang ginagawang unknown is this, no? The value of R sub t. This problem is a little bit simpler because wala kang RS. So since there's no RS, in this particular case, VG is actually equal to VGS. No? Because RS is equal to 0. So madali mo mako-compute for VG, no? Voltage divider dito. So VGS is just now 5 times 20 over 20 plus 30. Which is still 2 volts. That is still 2 volts. Okay. And then you have to figure out, okay, if this transistor is going to be in saturation, ano yung allowable values nitong R sub d? So I just leave that up to you. No? I just leave that up to you. How to determine the allowable values of R sub d so that this transistor will stay in saturation. Okay, I challenge you to solve these problems. If you want me to check your answers, you just send me your solution by email, and I promise you I will tell you if your solution is correct or wrong. No? Or if you're stumped, kung hindi nyo alam paano ituloy, At least show me what you tried to do, and then I will try to guide you to find the correct solution. So that's all that I think that practically, or that effectively covers everything that you need to know about NMOS for everything that you need to know about MOS transistors for EEE 1, 2, 3. We're not going to go deeper into MOS transistors than this. In EEE 131, I mentioned this last Tuesday. You're going to do more exercises with PMOS. In fact, NMOS and PMOS together, you call that CMOS, complementary MOS, when you have both NMOS and PMOS in a circuit. And CMOS is now the most common type of circuit that you find in integrated circuits or in microchips, CMOS. And then you have the depletion type also. The depletion type, because what we studied was just enhancement type. Okay, any questions? Any questions? Okay, I want to warn you that exam 2 is coming up. So after this, ang next na kukunin natin is digital circuits. That is next week. And then after that is already your exam. So you have to start gearing up for your exam. You have to start practice solving problems, taking a look at the previously presented material and all that. So yun lang, you have to pace yourself for your next exam. Okay, so that's all that I have for today. I'm going to leave when the last person leaves so that you can still ask some questions if you want. Thank you.
Thank you po, sir. Bye-bye.
Thank you po.
Okay.